Alright, we're going to take a few minutes now and go over power and energy. Okay, now those two go hand in hand, and sometimes they're a little confused about which one is which, so we're going to try and separate them out for you so you have a better understanding of the difference between power and energy and how actually they relate to one another. Alright, so power at its simplest is the rate at which energy is used or converted into a different form. Okay, if you're really powerful, you're able to turn chemical energy in your muscles into kinetic energy to run faster. Okay, or to turn chemical energy in your muscles to lift like a weight or a barbell higher. Okay, you're more powerful the faster you can do that. So cars with higher horsepower ratings, which is 1 unit of power, convert energy faster than low-rated cars. Okay, now it doesn't necessarily mean they go faster. They just can convert the energy faster. Okay, it all depends also for cars about mass and other conditions. All right, now the basic math behind power is energy divided by time. Remember earlier we said that energy is usually shown with a capital U. Sometimes you see it as a capital E. I'm going to use capital U because nothing else uses a capital U, so I want to keep it separated. And remember, energy can be any form of energy you can talk about with power. Okay, so the rest of this short little screencast, we're going to talk about electrical energy. But I could put kinetic energy in there for you. I could put potential energy. I could put chemical energy. I could put a combination of potential and kinetic. I mean, there's multiple ways that you could look at energy. For the beginning of this, since you're new to it, I'm going to keep it as simple as I can. But I just do want you to understand that you can be broader with that and use power in much more in different ways other than electrical. Okay, now the first thing is the unit for power. The base unit is watts. Okay, you would show that as a capital W. A watt is a joule per second. Joules divided by seconds. Okay, there are other forms of power that you probably see like in car commercials. Horsepower, for example, is another unit of watts. A kilowatt is 1,000 watts. So later I'm going to talk about a kilowatt in this little screencast, and that really just means 1,000 watts. Just like a kilometer is 1,000 meters, a kilowatt is 1,000 watts. Energy we're going to talk about in joules. Again, there are other forms of energy that you can use, like a calorie, a dietary calorie, like you would read on the out package for chips or cookies or something like that. That's actually a form of energy as well. And then time always is in seconds. Okay, so there are different units. We're gonna keep them strictly to watts, kilowatts, and joules, things like that. And I'm going to show you one specific one that's used for electric companies that I'll explain a little more in detail in just a minute. But we'll try and stick to watts or some form of watts. Okay, so let's just go ahead and try one. So what would the power be of an iPod charger that uses 30,000 joules of energy in 4 minutes? Now 30,000 joules seems like a very, very large number, but it may not be. Okay, it really depends on what you're doing, what kind of energy you're trying to convert. Okay, it might be actually a small amount. So this is one of those situations where I would tell you to just stop the video, try and do the problem. Alright, and then hit play again, and then we'll advance to the next one, and I'll show the work. Okay, so you should stop the video here, try it, and then come back to it. Okay, you should have stopped the video and tried the question, and it's a real simple one, but again, every little bit helps. So what's the power rating of an iPod charger that uses 30,000 joules in 4 minutes? You would take the 30,000 joules divided by the time in seconds. So there are 240 seconds in 4 minutes. So that gives you a power rating of 125 watts. Okay. Again, that is the base unit. If you wanted to, you can convert that to horsepower. That's not something we'll do just yet. But if you really want to know, 1 horsepower is equal to 746 watts. If you want to put that in your notes right now. So 1 horsepower is equal to 746 watts. It's just a larger unit. Very similar to the difference between feet and miles. Okay, it does come up occasionally, but not very often. Now, what does power and energy mean for your electric company? Power and electric companies charge you by the energy unit and not by the power unit. Okay, so even though it's often referred to as the power company, you're really looking at how much energy you get. Now, for American-based companies, they charge you by the kilowatt hour. So they look at the number of kilowatts you use times the number of hours that you use it. And the cost of it really depends upon the area of the country that you live in, and also whether you are a residential location or a commercial location. Okay, so for example, in this area, the average value that your parents would pay at home is about 14 cents per kilowatt hour. Okay, other places is more expensive, like for Hawaii example, where they have they have a harder time getting their energy because there's less plants and less places to produce it. Theirs averages about 22 cents per kilowatt hour. So they pay almost double what your parents pay here in Hawaii. Okay, now that may not seem like a big deal to you, but if you were to look at your parents' electric bills, that could be the difference between $300 every month and $500 to $600 a month that they pay just for the electric bill. So I want you to think about that a little bit when your parents are telling you to turn your lights off in your room, don't leave your lights on. Even things like keep making sure you shut the door behind you, closing the windows when the air conditioner is running. All those use more power. You use up more kilowatt hours of energy, and every little bit of that costs your parents money. Okay, and we're going to do more study of that as we go along, but just keep that in mind. So let's actually, I said that, let's take it a little further and let's do a question that deals with that. How much does it cost for your parents living in the Philadelphia area for you to leave your 60-watt desk lamp on all day for a 30-day month? Okay, so think about it like if you were to just leave your lamp on all the time for 30 days, and a typical 60-watt bulb, how much would it cost in Philadelphia? So we're going to use the 14 cents per kilowatt hour rating. Okay, now this is realistic. Okay, this is very realistic. This is not something that I have made up. I didn't doctor it for the sake of the problem. This is a very real value. Okay, so again, I want you to stop the video. Even though you see the answer in front of you, stop the video and do the work, and then progress on to the next slide, and you'll see how to do it. Okay, but you really should be practicing this on your own. Don't just look at the next video and copy down the work. It's not doing you any good. All right? All right, you should have stopped the video and worked your way through the problem. Now, this one looks a little more involved. It's really not. It just looks like a lot of steps because I was writing out all the work for you to see it. So it's still a power problem, and you're looking for the energy. So you have a power of 60 watts coming from your desk lamp and a time of 24 hours times 30 days. Okay, so you can see in the first line, I just have the main equation, the one that you would see on your equation sheet or on the quiz or on the test or whatever. The base one is P equals U over T. So what I did was, since I'm looking for energy, I need to first do the algebra, the simple algebra to get U by itself. So I multiplied both sides by T to get U alone. Now the power that I have is 60 watts. Now the important thing to understand is that you have to have it in kilowatts. Now remember what I said, there are 1,000 watts in a kilowatt. Okay, so when you're doing math like that, the very simply is 1,000. You would move the decimal 3 places to the left to get a kilowatt. Okay, there are 60 out of 1,000 watts there. Okay, so that's where the 0.06 comes from. If you don't quite understand that, just ask me in class or before school or whatever, whatever, and we can go over it a little more. Now the T part, remember, I'm getting the time from a whole day 30 times. So I'm getting 24 hours times 30. That's where that 24 times 30 comes from. So to leave your desk lamp on all month, you would use up 43.2 kilowatt hours of energy. Okay, now let's see how much that comes out to be. If you're using 43.2 kilowatt hours of energy and it costs you 14 cents for each one, you would just multiply the two together to get the cost of it. Okay, it ends up being about $6.05. So even though that may not seem like a lot, if that's just what it costs to run your lamp, start thinking about all the things that pile up that could end up costing quite a bit of money for the month. If you leave your lamp on, if you're charging your phone often, if you got your air conditioner running in the summertime, your refrigerator, if your parents have a freezer in the basement or in the garage, all those things really add up. Okay, they add up quickly, and you may not realize it, that $6 a month, okay, that's 6 times 12, that's $72 a year you would spend just leaving your lamp on. Okay, after a while, it starts to make a little more of a dent. All right. We're going to do more with this, but I think that was good for you to see, and I think it's good that you can actually see a realistic value from this. So in a realistic comparison, you might see those new curly Q-shaped, eco-friendly light bulbs that are about 20 watts, and they give off about the same light as a 60-watt traditional bulb, okay, because based on the way they work. They use less power, and they actually would reduce your cost by 66%. So really, if I were to replace in the last question we just did, if I was to replace it with a 20-watt bulb instead of a 60-watt bulb in my desk lamp, it would only cost me a third of it. So it would only cost me $2 a month to leave my light on all the time. Okay, now those bulbs are a little more expensive, but they also last a lot longer and they use less energy. Okay, so that's one of the small things that you could do in order to increase the efficiency of your house and save money. Okay, so I would encourage you to maybe go back over this a little bit. You heard a lot of things in it. Maybe fill in the gaps. And if you find questions you need to ask, don't hesitate to ask me in class, ask me before school, email me, something like that. If you can't find me, of course, there are always other teachers around that you could always ask questions about. But this is a really good topic for you to look into because it does have a lot of pertinence to your everyday life. Okay, much more so than, momentum or things like that. So this really is something that pertains to you every day, and you could really do a serious evaluation of your home at the cost. Okay, because every appliance that you find, there's a rating on it somewhere. Probably if you open your fridge or look on the back of your fridge, there's probably a yellow sticker that tells you how many kilowatt hours your fridge will use per month to turn it on all the time. If you know what model you have for washer and dryer, you can look it up easily, things like that. So really take it to heart and really try to evaluate how do you live your life at home. You don't necessarily have to change your life, just change it a little bit to accommodate these small differences that will end up saving you and your parents money. Okay?